Good morning, everyone. Today is May 30th, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. I am your host, Franklin Hu, and today we have Dennis and we have Bob. And so, what were you guys discussing a little bit earlier there?
Gyroscopes.
Gyroscopes. So that's a very interesting topic. So what were you talking about gyroscopes?
Well, Bob pointed out that Buckminster Fuller had an article that explained why if you push a gyroscope in one direction, it goes off at right angles instead. And it was didn't involve a lot of math, which is sort of amazing. And I pointed out that there was this guy R. Ubasimov, I guess it is, in Kyrgyzstan, who got himself a precision gyroscope and did some experiments with a stopwatch. They don't pay him much in Kyrgyzstan, of course. He didn't have a big grant. And he claimed that his experiments showed that classical mechanics was way off as far as that particular gyroscopic motion was concerned. And also there's Fran McCabe, M-C-A-B-E or something like that, who was an engineer. He's dead now, but he did a lot of experiments showing that classical mechanics seems to be way off when it comes to gyroscopes. And he has, even now, he has online, some of his stuff is still online. I suppose they'll take it down one by one, that's the way of the world nowadays. Don't refute people, just take down their videos after they die,
So how do you think did they actually come up with an explanation that made sense to you how a gyroscope worked? The mysterious thing about the gyroscope is that it keeps its position in space once you get it going. And that's how they detect, say, your orientation in the spacecraft, because you can move the spacecraft around. If it moves the gyroscope itself maintains its position in space. It seems to be very mysterious how it can do that.
Well, that is the key property of gyroscopes, is that the axes don't change unless you either force them to change, like in scissoring and Boeing IP, inertial propulsion, or you have gravity acting on them. You have one end fixed at the pivot point, and gravity acts, and it makes it precess, also not just precess, but nutate as well. And this is pretty well understood for simple things, but when you get complicated, like Fran McCabe did, or like Ubasimov, or however you pronounce it, did, then problems begin to arise. You don't get the right answer anymore using classical mechanics.
Well, this is kind of the way when I think about gyroscopes, I think of like if you took a bicycle wheel, say, and you roll that down the road. I think we can understand that that's just an inertial object moving forward, right? That it's spinning around doesn't necessarily make that much difference. And but suppose that while the wheel is rolling down, I sit there and I shove it, right? So if I shove it, it'll go in a different direction, but it will eventually right itself, right? There's a force that will cause it to. So if I try and shove it sideways, it will still continue moving forward, but it still wants to be, kind of upright. So it's kind of resisting, the forces that you put on it, because it wants to be, because it can only roll in a straight line if it's upright, right? If it's tilted over, it's going to be curving all by itself, right? I think. So I'm just trying to think that maybe that's one way to mechanically explain some of the behavior of of that, right? I don't know. What do you think?
Well, if you take a gyroscope in space that's spinning, and so its axis is not is fixed in space, and assuming it's not under any field, electric field, gravitational field, and so on, if you slap its axis with your hand, say, it'll engage in some transient behavior, but eventually it'll come back to having the axis fixed in space again. But the new axis may not be parallel to the old axis.
Yeah, that's true. I mean, it will twist in response to your force, but it will take a different thing. So that's like if you take a gyroscope and you stick it on a little pivot, gravity exerts a constant force downward, but it will translate around its pivot in response.
Well, it may nutate too, though. It may go up. The axis may go up and down, as well as sideways.
Well, it likes to try and keep the same axis is kind of the strange thing, right?
Yeah.
That's the gravity-defying aspect of this whole thing.
Hi,
James here.
By the way, Franklin, you're very out of focus today. For some reason.
Am I out of focus?
You were. It looks a little better right now, but you were quite blurry earlier.
Yeah, I was trying some other different things here. Let me see if I can reduce the bandwidth on.
Yeah, see, now you're really blurry.
Here.
And I'm wondering if it's just your motion. As soon as you go into motion, everything blurs quite a bit.
Yeah, because I've got another screen up here, and yeah, I seem quite blurry, right? I don't know why that is. So, is my internet connection maybe weak? No, I don't think so.
Maybe
I'm in the witness protection plan, so you can't see me, I guess.
That's pretty good.
Well, okay, so we got James here. So we were talking about gyroscopes. So I was wondering whether, James, you have any idea how is it the gyroscope can, say, resist the pull of gravity? You've always all seen, you put a gyroscope, you stick it on a string, and it just sits there and it spins around. It doesn't fall off like you would expect. Or if you have a gyroscope and you stick it in one of these multi-gimbaled thingamajobbers, you can spin it all around, but the gyroscope will still be, say, pointing in the same direction, no matter how you spin that thing around. So, James, I was wondering if you have any insight on how that works.
Well, I guess my only thought at the present time is that the translation of angular momentum into linear momentum, I guess, is opposing the gradient of the gravitational potential. But that doesn't seem like a very satisfying statement that I just made. So I think that needs a little thought. I think that needs a little more thought on my part.
Yeah, explain what we observe, but not too much about what's actually going on there. So I'm still trying to think, what is the spinning wheel doing? And why does it act the way it does? Why does it tend to resist any change in motion? I suppose, another thought that I had is that what's going on here, since I believe in an ether, that each of the atoms in the gyroscope is actually cutting through the ether which is present in space. And that's basically that's actually the storage device for inertia. For example, the interesting question is, where is the energy in a bullet that's in flight, right? I mean, we could tell where the energy is before you fired the gun. That was in chemical form in the cartridge. Okay, then you activate that energy. And there's a big explosion, so obviously there's a lot of energy there. But then the bullet flies out in the middle of space, right? And if you were to sit there and examine it, you would find out that it looks like a regular bullet, right? It's no different than the bullet that was in the gun, pretty much. It's all made out of metal, so there doesn't seem to be anything that's really different about the bullet while it's flying through space. But then it hits a wall, and then there we see, a lot of apparent energy when it hits the wall and destroys things. But when it's in the middle of the air, where is the energy stored, right? It's like a battery of sorts at that point, right? It's definitely got some kind of energy stored in it somehow. So the question is, where is that energy stored? And I'm claiming that the energy is actually stored in the blank space itself. That in order for the bullet,
that comment by Franklin does inspire me a little bit, because in your legacy quantum mechanics, if I may say a brief background, generally the system state is represented as in terms of position or momentum. The system state in binary mechanics includes both position and momentum. So when Franklin says, where is the energy stored, it's in my view in the configuration of M and L type quanta in the system state. That's where it's stored. Much like the spinning gyro, apparently most of the energy is in the circular motion of the in the proton and electron bit cycles. Okay, so and perhaps the bits are synchronized over gazillions of them, and that's why it resists change of position because of that. So where's the energy stored? In the system state, which is M and L bits. Okay, M and L quanta.
Yeah, now somehow I thought that you would probably figure out an answer based on your bit quanta, right? That's what you're supposed to do.
By the way, I don't want to change the topic at all, but just as a throwback to several weeks ago, Franklin's love for the analogy of billiard table, and the balls bouncing around, can be very useful. I was thinking after the presentation on the fine structure constant alpha that we could use Franklin's analogy that he likes a lot, and I think all of us can like it. Imagine two people with a billiard ball. One is the electron and one's a photon. Okay? They're at opposite ends of a billiard table, but there's a screen coming down. It doesn't touch the billiard table, but the two people can't see each other. Now, at a count of 1, 2, 3, each of these two individuals in a random direction sends the billiard ball flying, okay? And it's going to be bouncing off, as everybody knows, bouncing off the edges of the billiard table. Now, the alpha then is the probability that they will hit each other. Now, let's say you do 100 trials and only one time do the billiard balls actually strike each other before they come to complete rest on the billiard table after ricocheting around. Okay, so there's your probability alpha in a very easy to visualize experiment.
Yeah, I like that. That's an experiment that has certain probabilities, right? Because what's the probability?
Right, because you could say
fired randomly.
Sometimes the two balls could be ricocheting around, and never actually collide before they finally come to rest on the billiard table. So we mark that one as a 0 trial. Throw the balls again, and we just keep on counting. Of course, we know from statistical mechanics that the probability that the balls will actually hit each other depends upon the size of the table, the radius of the 2 billiard balls, and their velocity, how long they'll be ricocheting around, etc., etc. All of these kinds of things. But the billiard ball analogy for the probability of their actually striking each other in a particular trial, it gives you an idea of what the constant alpha means in terms of the so-called strength of the electromagnetic interaction with a charged particle. I thought that was a cute analogy.
Franklin?
Yes, Dennis.
There's an experiment done by Professor Alexander Dmitriev. He's a Russian professor at some university in St. Petersburg, and he had a massive steel plate on one hand, either the surface either being flat, either vertical or horizontal, and a small steel ball was either dropped on it if it was if it was the plate was horizontal, or else ejected against the plate if the plate was vertical, the surface was vertical. And he should have gotten, according to classical mechanics, the same result either way, because gravity, in the case where you're dropping the ball, the immediate rebound velocity after the collision and the immediate attack velocity after the dropping, their ratio is the coefficient of restitution. And you should have gotten, according to classical mechanics, the same coefficient of restitution, whether the ball would hit a horizontal plate or whether the ball hit a vertical plate, both times hitting it perpendicular to the plate. And but he didn't get the same restitution coefficient. So I did some simulations based on Newtonian theory, and was able to get some interesting results. I think at least Professor Dmitriev is looking at them. He thinks they're interesting. And these results were obtained by using variable inertial mass, which isn't supposed to occur in classical mechanics, but there have been some experiments by Eric Lathwaite and people like that indicate that it does actually occur sometimes. And so I have 4 appendices, 4.1, 4.2, 4.3, and 4.4, that are online on ResearchGate and also academia.edu, where I simulate that there's 4 cases because there's 2 impact velocities, and then impact can either be horizontal or vertical. So 2 times 2 is 4. So there's 4 simulations. And as I say, that you can get them for free on ResearchGate, or you can get them on academia.edu too free if you first pay to get on academia.edu, which is $100. So.
All right.
So could you summarize, Dennis, could you summarize, Dennis, the basic take-home message of these 4 simulations, please?
According to Newtonian theory, if you allow variable inertial mass, but change as little as possible of Newtonian mechanics with respect to that condition, that you have to be able to allow variable inertial mass, then you work it out mathematically, you get what's called Newtonian theory. Then you get either, depending on how you look at it, you either get the fractional increase in mass is dictated by the mass change function times the mass where it's not moving, the mass for no motion.
Wristband.
Yes, and so F then is what determines the thing, and it's you can expand it in three variables, Taylor series in three variables. One being the acceleration, the other being the time derivative of the acceleration, and the third being the angle between them. Then if you terminate that series after one non-trivial term, the first term is unity. If you terminate it with acceleration, a function of acceleration, a constant times the acceleration times the time derivative of the acceleration and times the cosine of the angle between them, and you terminate the infinite series after one non-trivial term, then you hope to get, since this experiment is not involving high velocities, but it does involve tremendously high decelerations and time derivatives of deceleration. And so I terminated the series after one non-trivial term and saw if I could fit the data using that with just one constant times those three variables. Then, and I found out that I could, but of course, there's only two velocities involved. There are actually four velocities in the experiment, but the other two, the results, the precision wasn't good enough to simulate them effectively. So I sent it off to Professor Dmitriev, and my simulation involving this termination after one non-trivial term, and he tells me he's looking at it, but unfortunately they've got the co-virus there too, and everybody is, it's causing a lot of problems, and so he doesn't know when he's going to be able to get back to me, but I'm hoping to hear from him one of these days.
Thank you.
You're welcome.
Okay, so we got a question here, which is, how does a laser gyro work? So I am going to see whether I can share my screen here. And this is the Wikipedia on how a laser gyro works. So what we have here is that it has two counter-propagating resident modes. So, and that's using, so it's got two light beams going in opposite directions. And when you rotate it, it can detect the rotation. So a ring laser gyroscope doesn't actually have anything spinning, but it can detect whether it's being twisted and having angular momentum. So this has kind of been a topic of discussion going on in the email, in that this basically shows that the speed of light differs because of the Signac effect, right? Some people would argue that you can see the speed of light basically increase or decrease in speed because it can detect these kinds of motions. If you send beams in opposite directions in circles, when you twist the thing around, it's like the beam going this way is going to have to go a little bit further than the beam going the other way when you turn it, right? Although personally, I think that's not really still not a case of variable speed of light. That is a case of variable motion of your sensors, I guess is what I would call it. Since I would be in favor of the picture that the speed of light is always constant with respect to any stationary frame, which is actually what Einstein was saying in his paper. If you read his 1905 paper, he mentions the stationary frame about 51 times, so it's not an insignificant concept. And that's the concept that if you are in you pick a frame, any frame will do, and you measure the speed of light from it, what Einstein was really saying is that that speed of light is independent of the speed of the transmitter. So if I'm sitting on the Earth and I see a car moving across the freeway and he turns on his laser beam and I measure the speed of light coming out of that car, I will find that the speed of the car is not going to be added to the speed of the laser beam, right? And it's not that if I were to measure the speed of light from something that was moving, like if there was a car moving at the opposite way, and if I were to try to calculate it based on, I don't know, like the relative closing or relative speed of that moving car, then I would find that that in that case, the speed of light would get added to the speed of the car. But that can only be done in the moving frame, which is in your stationary frame, which I know this is kind of confusing. It's like people get confused about it. But basically, I feel that the speed of light is like the speed of sound in air, which is relative to the frame of your atmosphere. And so that whole thing's not that mysterious. And that's how these ring lasers work, is that they're relying on that speed of light basically being constant in a stationary frame. So that when you move the frame, you can tell whether you're moving or not. I don't know if anybody had any comments on that. So,
well, my derivation from the, if I may, my derivation of the speed of light from nothing more than the time development laws of binary mechanics is entirely consistent, and it's several with what Franklin just said, and his analysis of that ring laser device, because you might recall when this was discussed some weeks ago, the quanta are emitted from one side of the simulated space. Once they enter the simulated space, what happens to them and how they propagate to the other side of the simulated space, where we can then measure the velocity of light, depends only on those quanta in that simulated space and the dynamics of their time development. It has nothing whatsoever to do with the object from which they were emitted, which is entirely consistent with Einstein's concept, and I've discussed this in at least one paper, and that Franklin just summarized.
Yeah, I think, see, the biggest violence to Einstein's work is the translation of his postulates to the effect that the speed of light is the same in all frames. This is what people say, that speed of light is the same in all frames, and that's not what Einstein said, and that is complete nonsense, because that's, if you say that the speed of light is the same in all frames, then, if you have the two cars moving at each other and you're measuring the speed of light in the moving car, then it would say that the speed of the moving car isn't going to matter, right? But it does matter. I mean, if you do that, you will find that, yeah, it takes light less time to travel that space because your car is moving. It's gonna meet. It's like moving the goalposts, right? And it's
the exact thing that I think Franklin is saying, if I may, is let's take my simulation experiment again, where it's very simple. We inject quanta on one side of the volume and sense its arrival at the other side, and measure the distance traveled and the number of simulator ticks, which translates with the fundamental primary time constant into a time in seconds. We get the speed of light. Now, obviously, if we were traveling as Franklin just described, in a vehicle or a little car or something through the simulated volume along with the quanta as they move from one side to the other, it would appear that the speed of light is zero. I mean, if we were, traveling at the same speed in this simulated volume in a little car, the quanta wouldn't appear to be moving from right to left or left to right at all, would they? I mean, it'd be zero.
Yeah, so that would be like the non-stationary frame. That's why it's important to pick a particular frame. This is the other thing that I think gets really confused as to whether there's a preferred frame or not. And I think in Einstein's work, because he referred to stationary frames so much, that there is definitely a preferred frame, that frame being the frame of the Earth laboratory, for example. That's would be the preferred frame. And so you stick with that preferred frame, and then you do your experiments based on measurements from your preferred frame. You don't do your experiments relative to two different frames, right? You don't take a moving box and the stationary box and then try and figure out what the speed of things are by looking at the moving box, right? That's the moving frame. That's not proper. But I think that all theories like James's, which propose that space has got something in it that light propagates through, just like my ether theory would say basically the same thing. That as long as there's something there that is actually being the medium for propagating things, just like the air is the medium for propagating of sound, that there is some other medium that is propagating and controlling the speed of light.
And that, of course, in binary mechanics would be the model of space, which is a cubic lattice of a spatial object that I call the spot cube. If I may add just a little editorial, which may be a little bit of a side road here, I think what Dennis Allen just presented a while ago, and I have to read those papers very carefully because Dennis has posted them on ResearchGate, along with the work of Dmitriev, my work, is just a guy with a computer or with some very simple apparatus in his garage practically. And you don't even need all these multi-million dollars worth of funding, which seems to go nowhere, at Fermi Labs, CERN, and et cetera. So that's my little editorial to basically applaud the creativity of individual open-minded researchers. And for the listeners here and in this chat, all of you can do this. I mean, if you're listening to the chat, you probably already have a computer, right? And you can do experiments. You don't necessarily need multi-million dollars to do these things. That's my little pep talk for the day.
We had a comment here saying that James, that's the Newtonian theory, but it turned out that measurements didn't confirm it at high speeds. What do you make of that comment?
Well, I don't know what experiments he's talking about, or number one, or number two, what I said is equivalent to the Newtonian theory. Yes, I use force E equals mass times acceleration a lot in several papers, but so I don't know how to.
Talking about relativistic mass increase, perhaps, right? So how does the relativistic mass increase happen in your model, where as the a physical particle, not a light wave, but a physical particle accelerates close to the speed of light?
Oh boy, you've turned me on. This is the big scandal at CERN. Okay, my work in a paper called Energy Elementary Particle Energies which has been extremely popular in recent months since I updated it, shows that when you take these protons or electrons, let's say, and accelerate them toward the speed of light, you're talking about energies 10 TeV. That's, I guess, what? TeV is what? A trillion electron volts, or whatever the TeV part means. When you get to those high energy levels, you don't have protons anymore. You have a soup of quanta. You have what I call a lepton quark soup. They call it quark quark gluon soups, which is a misnaming, but that's not the big issue here. The big issue is still, I went on Twitter the other day and saw some reports from the CMS experiment, which is a National Science Foundation that's in the US, funded to the tune of over $20 million. And they're talking about proton-proton collisions at 13 TeV. 13 TeV. That puts, and if they do the calculations, they're within 99.95 or some almost 100% the speed of light. And they're characterizing these as proton-proton collisions. There are no protons at 13 TeV. All you've got is a beam of quanta, which is in the soup range. There are no defined particles. You're almost up to the 100% possible quanta density, and yet they're talking about building an even large circular accelerator over there in Europe. As everybody here knows, they're talking about digging the tunnels, and Elon Musk wants the contract and so forth. They've already reached the limit, and they don't have. So they're telling us they're doing proton-proton collisions. There are no protons at that energy level. It's just a soup of pure energy quanta, which is completely undifferentiated energy, pure energy.
So I don't know why you would say that. I mean, I'm not sure how that even follows from your theory. I mean, the proton is just the spot cubes that have this particular pattern going on in them, and that thing is just moving at the speed of light. I don't know why that would change it from a proton.
Well, the cube doesn't move at the speed of light. What moves is the quanta from cube to cube.
Yeah, the
quanta. And if you get up to 100% saturation of the what I call the bit loci, I probably should call them quanta loci. It'd probably sound better. But when you get up to 100%, there's nothing defined there.
Well, why would it go to 100%?
There's the electron and there's a proton. It's just pure, total energy quanta, completely saturating a unit volume. And that's what they've got in their beams. They don't have protons there.
I don't know. I think they do have
differentiated there.
I'm pretty cool with that. See, I just don't understand on your theory why you would say it would be a bit density quanta increased to 100%, because if you have a single proton running through space, the bit quanta density is constant, right? It's no matter how fast it's going, wouldn't it?
Well, no. The whole velocity, you have to add quanta. Remember, the L-type bits represent future motion. That's how binary mechanics represents in the system state mathematically the both position and momentum at the same time, unlike legacy quantum mechanics. And I say legacy as if it's way in the past, but that's what they're doing now. Okay. Now, so there's a nice graph. I actually showed it in a presentation, I think on maybe I didn't, but in the video on CERN, scientific merit that I have, it goes through this, and it points out that as you get up to 100% bit density or quanta density per unit volume, what could possibly be differentiated? I don't know much about astronomy, but it just pops into my head where people are talking about neutron stars, where they're just all neutrons. Well, there's nothing differentiated there. It's just like, you can't say, well, here's a helium atom over here, and we have a proton over here. No, what they're saying is they're all neutrons. There's nothing differentiated there. There are no helium atoms there, or iron atoms, or anything else. It's just pure neutrons, according to what the astronomers tell us what a neutron star is supposed to be. And
that's
true.
That's interesting topic. Although getting back to what's going on in the CERN accelerator, so I would argue that that's not true. I would argue that the protons do still behave as a point particle, as in they are tracking these things, and they definitely see something happen. When they collide, they produce a gigantic shower of other particles, all of which are trackable. So it would seem that the proton itself still appears to maintain its structural integrity, as in, a lot of these protons will fly past each other and not interact still. But a few apparently have these head-on collisions. Now, if they were nothing, then I would say that they could probably accelerate the beams against each other all day long, and they would never collide.
They're nothing. The beams are 100%, or nearly 100% maximum density of energy quanta. So there's nothing differentiated in there. And yes, what you said is correct.
Then there's nothing to collide.
When they collide it from opposite directions, as they do there, you get all these jets and a huge event, with all kinds of things flying out. Well, that's as the concentration decreases. These jets are, in fact, what's going on in these jets. The concentration of energy quanta is decreasing. And as it decreases, they start to see, oh, we got some bottom quarks over here. And there's some charm quarks or some pions or whatever. Sure. But see, the logic that you say, just because you see these jets occur does not mean that individual differentiable protons, and by the way, there's in the standard model, all the theories that they're using concerning the characteristic of a proton, and they actually say in their paper, you can read it in the tweets, just go to Twitter and look up CMS experiment, and they say it right there over and over again. We have proton-proton collisions at 1310. It's a complete hoax. They're either completely unaware of what they're really doing, or they're just simply lying. Let's just say that they're unaware. Let's be charitable.
It's probably because no one can see a microscope, and I mean, all that you can really tell is what's going on in your detectors, right? Something happens, and you see stuff happening in the detectors, and they try and trace back what happened, and definitely what happened in a very point spot. I mean, that is quite apparent, right? It's like an explosion. Out of a single bit of piece of space, we see like this explosion of particles. That we see with absolutely no doubt. Me personally, I think it's because, I don't believe that the proton lost any of its integrity. I'm perfectly happy with the proton being accelerated to near light speeds. But the question is, what is actually going on there? So I would say that, the proton, I think, just, we cannot tell. I mean, it could be what you're saying, could be, but I prefer to think that the protons did really not change. But there is that question of, from a point of mass, right? Mass increases. The proton at these speeds might be, say, as heavy as, say, a uranium atom or even more, right? So what that means is that it's just harder to push it any faster. Now, from the dissident community, it falls into two kind of categories, and that one of them is that the reason why you cannot accelerate it faster is simply because the thing that you're accelerating with only goes the speed of light. So that just puts a limit on how fast you can accelerate something, and then no matter how much you try to accelerate it with however much energy, that it's never going to go faster than the speed of light, right? If you have a car that can only push 30 miles an hour, you could line up 1,000 cars, and you're never going to be able to push anything faster than 30 miles an hour. So that
there's a very key statement that Franklin just made. I think when you've accelerated something, a particle, what you call a proton or whatever, up to about the speed of light, you've added energy to it. Yes. And what that means in terms of a quantized, a full quantization scenario, such as what I like to pursue, is that all of the quanta locations are filled. So there is then no more differentiation. It's just pure energy. Imagine I have a grid in which such as...
but I'm thinking that's where your theory fails.
Newspapers. Okay, let me just finish this one little point. Imagine I have a grid, a two-dimensional grid, and there's either a dot or not a dot in each little square on the grid, and you step back and you look at it and say, well, there's a face. Or I see a tree, or it's a picture of a car. Well, all of the newspaper photographs back in the day when they were printed and so forth were composed of these little dots. Now imagine every single place you could put a dot has a black dot. Well, what are you going to see? You're just going to see a black image, a blackness. You're not going to see any image of. There's no faces, no more cars in there. There's nothing. It's just pure dots. And so if I were to say, well, there's a face in there, you'd probably say I'm crazy. No, it's just a piece of paper completely covered with black ink everywhere. And I insist, no, in there, there's a proton, a picture of a proton. I think, give me a break. It's just contrary to even the simplest common sense. If you fill up all of the little dots with black ink, you just have pure black ink. There's nothing differentiated there. There's no.
Yeah, but this is where I think your theory fails, right? Because your theory is making a specific prediction that at the speed of light, the page will be completely black. But if we look at the actual experiment, we can still see the face. So it couldn't be. So it would seem that your experiment is predicting the wrong thing.
The only thing they see is when the oppositely rotating beams collide, and at those levels, you're up to pure energy.
No, it couldn't be pure energy because these collisions happen out of specific spots.
Out of that, you get all kinds of particles and jets. Literally thousands of events which cascade down, and the bigger, fatter ones break up into smaller ones, and finally, down to muons and so forth, and electrons and so forth. So, but the beams, you don't know what's in the beams if they're entirely saturated. Just like if I splash black ink everywhere and fill every dot location on a piece of paper, there is you can't see a face in there. There is no face. There is no proton in there. It's just
we saw the face. It shows up in the collision.
Energy beams.
We saw the face. It shows up in the collision. That must be because two faces slapped together, right? That wasn't two nothingnesses slapping together. There was definitely two things heading in the opposite direction that blew up.
Pure energy soup beams. Yes, I wouldn't object at all to what they're doing if they just told it like it is. We have undifferentiated at those TeV levels. We have undifferentiated pure energy beams colliding, and here's what we get. We get about anything under the sun you can imagine. That's what we get. And that would be no surprise, would it? Now, if you start to lower the TEV down, like in the older experiments or even present experiments where they're using less energy beams with a lower energy level, like I'm going to strike a proton into a gold or an iron nucleus and see what happens and blah, blah, blah. Okay, I can start to believe, yeah, you're striking a proton into an iron nucleus. Fine. But when you get up to 13 TeV and you get up to 99.95 or 99% the speed of light, you have saturated the energy per unit volume to the point where you just have pure energy beams. And I have no objection if they want to say, which by the way, which means they've already reached the limit. They don't need to build a larger accelerator like they're planning over there at CERN, one that's so many kilometers wide and so forth. 10 kilometer diameter. They've already reached the speed of light, essentially, which would be a pure energy soup beams. I mean, that's just simple logic.
Well, like I would kind of agree with you that I'm not sure that there's any point in building a larger collider, because basically, like you said, the same thing.
Agreed.
Get more of the same, pretty much, right?
Agreed.
It's like you're just shoving a bunch of energy. And we get out gobs of positrons and electrons, and few of those might make a heavier particle on occasion. But mechanically, you're just going to get more of the same, I would think. Right now, they're thinking that I was watching this program on the colliders there, and they, before they had found the Higgs, their worst nightmare was that they would find the Higgs and nothing else. Now, come, years after the discovery of Higgs, it turns out this is true. This is their worst nightmare has come true. That the only thing that the LHC has been able to find is just the Higgs particle. They are expecting to find all these supersymmetry particles, and no, they haven't found anything, right? So they're trying to propose to build an even bigger experiment in the hopes that, well, maybe this time we'll go find it, even though there was no real reason why they shouldn't have already found these things, right?
That's right.
Personally, I'm thinking that the Higgs particle, watching this program, they said that the Higgs particle just happened to be in a sweet spot of detectability, that because of its particular mass, that they can observe it in several different ways and they can confirm it in different experiments. And it just happens to be very convenient that it happens to be in the most observable spot. Now, for me, that sends up a lot of red signals saying that, well, maybe the reason why you detected something was simply because it was the most observable thing you could possibly have, right? Given your setup. So it was like almost inevitable that if you were looking at all the energy ranges, that you would see this little bump that, there's more here than you expect. Why? Because was there really something there? I mean, definitely according to your experiment, there was something there, or was it just due to the fact that it's just the most observable particle you could have possibly observed, right? That's the red flag to me. It's like, did they exclude that possibility? But the only reason why it was observed was because it just happens to be the most observable thing, right? And so more things got into its bucket than anywhere else, right? Because it's just easiest to explain, to observe something at that 125 gigavolt mass, right? So I still think they found nothing. I mean, personally, the whole idea, the Higgs particle is just some short-lived object, which is the result of the things in the Higgs field. I mean, the thing that makes up the Higgs field that's what's actually important, right? The Higgs particle is just something they theorize might happen if you stuck enough energy into space, that it would generate this particle. I'm not even 100% sure how they decided that.
Here's a few thoughts about that, if I may. The so-called Higgs field is actually has 4 real parameters in it, 2 each in 2 complex numbers, which are thought to be orthogonal to each other. Well, guess what? I have mapped from classical quantum theory the complex amplitude, which is a complex number, to an object I call the spot unit, which contains an M and an L type quanta or bit, which can only be 0 or 1, each one of them, to quantize energy. Now, in the model of space, in the spot cube, one can easily see that, say, in the electron spot, for example, there are 3 spot units and they're perpendicular to each other. Okay, so this is an approximation to the math that is used to describe the Higgs field. So in other words, the Higgs field is the best they could do with ineffective math. Math is not even able to represent both position and momentum simultaneously in a system state expression. Okay, so they can't even, represent the full picture in one mathematical expression. And so they're using very primitive tools. And so the best that I can say about the Higgs boson and Higgs field work is that, it was sort of a good effort given the limitations that they had, and it sort of provided a little insight, but it really is completely archaic and obsolete at this point in time, when we now can represent in an irreducible representation both position and momentum simultaneously in the system state, and define time development laws that are appropriate. The second point I wanted to make is, maybe someone else here is more up to date on this than me, but I looked briefly at some recent publications and material about the Higgs boson, and it supposedly decays into, guess what? D-quarks. It decays into quarks. So that's the best they can do, and I mean, it just shows you that if you're trying to drive a nail into a piece of wood, and you're using a hacksaw, a tape measure, and a screwdriver, they're all professional tools, but you're not going to get the nail driven into the piece of wood ever. You're going to need a hammer, a different tool. So my premise, to summarize what I just said, is that they're using primitive math tools which are unable to be effective, and they're inappropriate and inapplicable. So they're not going to get very far ever unless they go for full quantization. With full quantization, the whole world opens up as far as I'm concerned. That's been my experience.
The other thing that struck me about the discussion of the Higgs field is that, they're perfectly willing to call it the space molasses, right? Because this is how they provide an analogy to how it creates mass. So if you have this space molasses, their term, if you try and push a ball through that, then you can see that it's going to resist the acceleration, right? But if you still ask them, what is the space molasses, basically they don't have an answer. That's kind of contrasting, what is this Higgs boson or particle that they found, right? It's not actually what the space molasses is made out of. It's just a consequence of that thing being there, right? But obviously the Higgs field could not be made out of Higgs bosons, because those things decay almost instantaneously. And as far as I know, they decay into a positron electron, which once again is just like the easiest thing for these experiments to detect. And so they're just looking for positron electron decays that are more than a background, right? Because see, the funny thing is that they can measure the positron electron, and these things decay at any energy, right? If you draw a curve, you can see that there's like an exponential curve. Like any energy, this is how much decays, right? They kind of ignore all of that, right? Or they don't think that, you know, the reaction over here was a result of a particle per se. That's why they call this bump hunting. That in the smooth curve, there's a little bump up more than you would expect from the set of data, but it's not doing anything special. We just think that because there's more of them in one spot, that there must be a particle behind that, which I think is a lot of hooey. So going back to my personal theories, which, so I think that space is filled with positrons, electrons. They're just chock full of these dipole particles. So what you're really seeing that when you can collide these two protons together, and unlike James, I would have to disagree with him that they somehow become undifferentiated, because I think that based on what we see going on in the accelerators, that there's definitely still point particles in there that can be tracked in space and time as they go around. So we have to disagree there. But what I think happening is that what you're seeing is that the two particles come together, the kinetic energy is just ripping out all of the positrons, electrons that are in space. And that's why when we have these collisions, that's like 99.99% of everything we see, which is positrons, electrons flying everywhere. Now, sometimes some of them recoalesce into other things, like they could recoalesce into, I don't know, things like muons or neutrons or protons, but usually they recoalesce into something that also decays very quickly, like, for example, these Higgs bosons, right, which would have to be some combination of like 23, for example, I'm not sure what the exact number is, but it would take like 23 electrons of positron to come up with a mass for this Higgs boson. It's like you take something that big and then you predict what it would fall apart into. And then that's what they measure in the detectors, and then they go, aha, there must have been a particle there that was the result of all this decay, right? No one has actually ever, seen or measured a undecayed Higgs boson. All you can do is just look and see what fell apart and kind of work your way backwards, right? But I think that's a lot of hooey. So that's the other reason why I'm skeptical about building more larger colliders, because all you're doing is you're just ripping these positrons, electrons out of space. And basically what you've got is a positron electron generator. That's all you're doing. And all you're going to do is you're going to generate more positrons, electrons, and more energy you stick into it. So not a great... it's not very hopeful that you'll find anything more. Plus, the disaster of them not finding any other particles also says that there's really no incentive to build something bigger, but you have no evidence that building something bigger will help your problem. So
it really lines their pockets, though, Franklin.
It does line their pockets, though. But I'm thinking that they're probably not going to get away with it this time, right?
Oh, they will. I bet they will. The only thing that can stop them is that if the European Union goes belly up economically, then that'll put an end to it.
Yeah, maybe that could be another COVID victim here, right? Gigantic accelerator, right? So we got some comments here. Let's see here. We got a comment from Michael here. If the ether is rarefied enough, the photons of light measured by Michelson Morley don't interact with it because there is no inertial interface between photons and ether. Ether not disproved. Oh, well, that is a different thought. That the ether is just super rare, right? So basically the light won't be interacting won't be basically entrained or caught up or controlled by the ether. Although my comment about that is I think that the ether can't be rarefied. It must be really super dense, because we're saying that the light as a wave has to be transmitted through that ether. And if it was really rare, then that tends to slow down the speed of a wave, right? The speed of a wave tends to increase with density, because if your particles are this close together, very close together, then it takes very little time to make a propagation. But if your particles are way far apart, then they have to go all the way over here before they can go on, and that makes the propagation speed much slower. So I would see how fast light propagates. I mean, you need a medium. If it were compared to sound waves, something several million times denser than steel, actually, to get the speed of light to be. If you were to get the speed of sound to go as fast as the speed of light, you would need some material having millions of times density of steel to do it. So I would kind of disagree with that. And we have another comment. And if anyone else has any comments about my comments or their comments, just feel free to break in. We have another comment here, and said, indeed, for me, the optical gyroscopes, such as the laser gyroscope, demonstrate there's something in nature independent of the apparatus that controls the speed of light. Yeah, I would agree with that. There is definitely something that's independent of the apparatus that is controlling the speed of light. And the fact that things are in motion, actually, in the case of the laser gyroscope, isn't really counting. It's really that you're thinking that there is some reference frame inside the laser gyroscope which remains fixed and can be detected when you rotate the lights around, right? It says the speed of light is not determined by the apparatus, and of course also not by a distant observer. Probably also true. I'm thinking that speed of light is determined by I would say there must be a preferred reference frame, actually.
Yes.
Or you could pick any inertial frame, as Einstein did, right? As long as you're in a constantly moving, non-accelerating frame, then that's as good as if there was a true preferred frame. So, for example, in my theory, I think space is filled with positrons and electrons. And those positrons and electron field can be moving relative to me. I mean, it could be moving relative to me in this room. But there would, in fact, be one frame that you could pick where those particles are not in motion, right? That could be, and that's what would truly determine the speed of light. That if you were to measure the speed of light in that frame, you would see that it's constant every which direction. It doesn't matter what the direction of the receiver is or the direction of the emitter is, that the speed of light is going to be the same, just like the sound waves are in my room, right? But then we have this little tricky thing that it would seem that, according to all these light experiments, that the Earth is fixed in space, and we can only detect the 24-hour rotation of the Earth. So the geocentrists like that, because it's like, okay, yeah, the reason why we don't detect the motion of the Earth around the sun is because it's not moving. But yet, that's what they say the GPS satellites would tell you. GPS satellites would tell you, yeah, the Earth's not moving, but we only detect the 24-hour rotation. That's the only thing we have to compensate for. Other than that, the Earth appears to be fixed in space, not moving. We cannot detect its actual speed.
That's not what Ron Hatch said.
Here's an out-of-the-box thought. Oh, go ahead, Dad.
Ron Hatch, who was a GPS guy, invented the Hatch filter that really made it work. If you look at his paper, A New Theory of Gravity, and some other words, then it's 2007 physics essay paper, A New Theory of Gravity by Ronald R. Hatch. He points out that that you do have to take into account the Earth itself. But if you take things properly into account, you can synchronize throughout from the Earth into nearby planets and comets and whatnot. But he does not go along with the idea that the Earth is fixed. It's just that he wants to relate, GPS people want to relate everything to the Earth because we happen to live on the Earth. But the idea that the Earth is fixed as far as GPS people are concerned is incorrect. And if you look at Ron's paper, 2007 Physics Essays, A New Theory of Gravity and so on, then you'll notice that. He also shows that general and special relativity are wrong too.
No, I think that my claim has always been that if you read Einstein's papers without any initial biases and actually paid attention to what he says, then I claim that that's absolutely true. That's always been my little shtick. I say Einstein's right, but the problem is that what they're showing wrong is everyone's really bad interpretation of Einstein's paper, which says that the speed of light is constant in all frames of reference. They sit there and they disprove that. And it's like, yeah, that's easy to disprove. That's completely wrong. Of course, it's just not what Einstein said. Einstein never said any such nonsense. Speed of light is constant in all frames. That's ridiculous. It's such a violence to the language. It's unbelievable. So. But as you said, I think it's a very hard swallow for people to say that the Earth is like fixed in the cosmos. The only thing that's not moving. That's the essential point of view. Who don't like that, and I'm sure I don't like that. We have to figure out some reason as to why that is. And the alternate theory is that the Earth has its own little bubble of ether around it, right? So we drag our bubble of ether around, just like we drag our bubble of atmosphere around the Earth. And that's why we don't measure a difference. Of course, that bubble will have to extend out to, say, the GPS satellites in their orbit, right? And that's quite far away. So I would think that we would be in the interface zone at the speed of at the height of orbital satellites, but maybe not.
Well, they've sent probes out into beyond the farthest planet, and they've synchronized them. Einstein's special general relativities are falsified in that paper Ron I mentioned, Physics Essay paper 2007. A New Theory of Gravity, and some other words. It's not a hard read either. He was an engineer more than a physicist, and he explains himself pretty well. I think you won't have to know all kinds of tensor, four-dimensional space-time tensor theory. He just explains it all. It's fairly
I'm
simple.
just saying that everybody who is disproving relativity is disproving their own theory of what they think relativity means, and not strictly what was written by Einstein.
Well, Hatch understood what Einstein was saying, and in my opinion, so that's, in my opinion, incorrect, frankly.
That's why my opinion is so weird, because I'm thinking that everyone's opinion of Einstein is wrong, and that's what's actually wrong, right?
Yeah.
It's kind of a weird standpoint, right? It's kind of like I'm sitting against a dissident community in this one, right? Because I'm saying you're wrong because you're misinterpreting Einstein, right? You're putting up a straw man and disproving it. That's what you're doing, right? But if you look strictly at the time or the mass dilation formulas, those have been empirically proven. You can't say that those are wrong.
Well, Don Lincoln claims that there is no true mass increase with velocity. He works at the Fermi Lab. He's a more senior guy at the Fermi Lab. And he says what's actually going on is it appears that the inertial mass is increasing, but that is not actually the case. And if you if you search around a little bit on the internet under Don Lincoln at Fermilab, you'll find his various papers where he points that out, that there is no true inertial mass gain. It's just an appearance.
Well, you say inertial mass, and see, this is the way I think about it. I mean, if you think about inertial mass as being, I don't know, the actual amount of matter, right? And instead of talking about mass, let's talk about matter, right? So matter being the amount of stuff. So if I have 1 grain of sand, I have 1 unit of matter. If I have 2 grains of sand, then I have 2 grains of matter. Now, if I sit there and I accelerate my grain of sand to the speed of light, the mass will increase to like 10,000 grains of sand, the mass. But the matter still remains 1 grain of sand, right? That's what the matter.
But there's a paper, Relativity in Classical Physics, by Theodore Thorensen, on July-August 1995 issue of Galilean Electrodynamics. He was the chief theorist of NACA, which was the forerunner of NASA, NASA. And this paper was published posthumously by his daughter, or well, one of his kids anyway. And he points out that you can't accelerate using electromagnetism. You can't accelerate a particle past the speed of light, but if the thrust is from within, like inertial propulsion, then you can go faster than the speed of light. And I think this impacts James's theory too, because for him, there is no going faster than the speed of light.
So James,
well, if I may respond to that, I've got a whole paper on mechanisms of faster than light transmissions, and in my most recent paper titled Light Speed Derivation, it shows that there's always a few quanta that arrive before the major wavefront of the quanta as they transit the volume from one side of the simulated volume to the other side. And so, there's another paper called Faster Than Light, where the specific mechanisms of that faster than light motion of quanta, at least in one cycle or 2 cycles of the time development laws, can occur. But it's not very common, but it does occur. And every time you do this experiment with my simulator, you see there's always a few quanta arriving before the main wavefront. And that's because of this mechanism of faster than light possible motion of quanta in the time development laws. Now here's a question
where they actually showed that, I think. I'm kind of wondering about this, the reference I'm thinking about. But they did something like they did a pulse of light, and when you send a pulse of light, even though it might look square at the beginning, but as it travels through, when it gets received, it doesn't get received all at once as like a square, on or off. But there's always this leading edge where the intensity is increasing. And I think they're saying that leading edge actually, arrives basically faster than the speed of light, similar to what you.
Well, that would confirm my experiments, that interpretation. You see, like with the speed of light, they and in my light speed derivation paper in this year, I think it was recently, you'll find it right at the top there somewhere in the Journal of Binary Mechanics, that they talk about, like, for example, the front velocity, which if you have this little silly picture of a wave packet for a photon that you see in all the physics books, there's your photon, it's a rising wave and then it declines. You can talk about the front velocity where it just arrives. and that's the velocity basically that I'm measuring. But even before that front velocity, there's a few bits that arrive before that, and that's you're faster than light. Now, I don't want to change the topic, but if there's anybody with astronomy knowledge here more than mine, it occurred to me with this whole discussion we've had recently of inertial propulsion, and mentioned a little bit today also, is isn't the Earth like a huge gyroscope that's spinning, and therefore there should be a precession in its orbit to some extent? I mean, has anybody looked at this? Some of the other planets, measured in Earth days, one revolution might be hundreds of Earth days. Like I think one of the nearer planets, whether it's Mercury or Venus or whatever, and so their gyroscope, if you will, the whole planet as a gyroscope, if you will, has less angular momentum, you might say. So there, you would think there would be less inertial propulsion precession in its orbit. I'm wondering if astronomers have ever taken this into account or tried to.
Yes, precession of the equinoxes. Precession of the equinoxes.
But have they related it to the whole concept that the whole planet is a giant gyroscope?
Yes, it was done by Newton, and Newton considered the planet to be a gyroscope.
Well, thank you.
Yeah, we're definitely a gyroscope wobbling on its axis. We're definitely perceived. We definitely have that precession going on. It takes like 22,000 years or something for it to go all the way around. So this causes subtle changes in our weather. So that definitely happens here. Let's see, we still got some other comments here. Let's keep on going down the line here. Now here's the interesting one. It says there are objects in space measured moving 6 times the speed of light. So how can we tell the energy in those objects measured in respect to what? Oh, well, I haven't heard about objects in space moving at 6 times the speed of light. The only thing that I've heard close to that is that if we are in an expanding universe, then the edge of space is expanding of light activity here. Okay, I'm back. All right. Did I lose you guys for a second there?
Yep. Say that again, man.
Now, what I've heard about is that they're saying that at the edge of space, if space is expanding from the Big Bang, that those edges must be moving at faster than the speed of light at some point. Although I've never heard of anyone measuring objects in space moving faster than the speed of light. So can't really tell you how that would work. But he's asking, how can you tell the energy in those objects and measured in respect to what? Right? I still think it's still F equals MA. And that kinetic energy is 1/2 mv squared, right? So I would still think that those would still apply. And I would say that we have not measured objects moving faster than the speed of light, because we know that if we do find that it gives us, it actually creates a shock wave. And they call that like Kurzhessen's radiation or something. This happens all the time in nuclear reactors. If you look at a nuclear reactor, you look in the water, it's glowing blue. And that's because particles, I think the alpha particles, are actually traveling faster than the speed of light in water, because water has a certain speed of light, slower than in vacuum. But in nuclear reactors, these particles are actually able to exceed the natural speed of light in water, and it creates this shock wave, which we see as a visible blue shock wave. So if there was some region in the universe which was going faster than the speed of light, I would think we would have to see that blue radiation, and I don't think we have. So I don't think we have that much evidence for anything going faster than the speed of light in the universe there. guess that would be my comment on that. So we got a comment here. I don't know what a difference in prediction between what the experimenter expect two protons colliding and how James formulates it. I think that is what Franklin has in mind. Yeah, that's kind of what I have in mind. That I think mechanically you can model 2-point particles. Of course, if they're really a point particle, then they would never collide because point particles have no volume. But so they have to presume that the proton has some volume. I think we don't think that the proton is a point particle. We think it does have a finite radius, and it's been measured. And based on that, they can make predictions on like what they call the luminosity, right? Luminosity, which is the number of collisions you get, does depend greatly upon there being actual particles there. Right? So there's a lot of math behind those experiments, and that's what.
Why does it depend upon that?
Because the bigger the particle, it changes the frequency at which you expect them to collide, and they can predict this rate of collisions very accurately. It's not like a random guess. And it all works back to what they think, what the finite size of the proton is. So
that's what my whole model of the proton is based upon.
Pardon?
That's what my whole model of the proton is based upon.
Yes, and it could be your whole model of the proton could be wrong, and then that's always a possibility. I mean, my model of the proton is not anything like your model of the proton. My model of the proton says proton is two positrons and electrons glued together. That's what my model says. Your model says that the proton is this particular pattern in your spot cubes. Now, either of us could be wrong, but I can't say that your theory is wrong because my theory is right. That would be ridiculous, right? But neither of us can say that what
it's really how much
wrong either.
It's how much data we decide upon different models. I think, in terms of how much data is in agreement with the model. Like, for example, my model of the proton predicted back in 2011, in fact, that the proton had a non-spherical shape. Some years later, accelerator guys came out with a paper saying that their scattering data suggested that the proton, in fact, had a non-spherical shape. So you see, we decide upon model A or model B based upon what it predicts. And does it predict things accurately
what your
or
model
not?
Predicts is that what your model predicts that at high speeds the proton disappears. That's what your model predicts.
Not disappears.
That is your prediction.
Okay. If we have a picture made of little black dots, like in the old newspaper photographs, black and white photographs, and
so the pixel disappears. That means the proton disappears. It's undifferentiated from the background. That's what you're.
There's still quanta there, but if you fill in all the places where you could put a black dot, then you just have a black picture. In other words, there's nothing differentiated in there. So I don't see why there's a problem with that. I'm not saying that there's nothing there. Right? I'm saying that there's everything there. If the quanta density is nearly 100%, there's no particles differentiated in that. I don't see why that would be a controversial idea, frankly.
Because at that point, you couldn't localize the proton. You couldn't say that it's in this specific coordinate system, X, Y, Z. There it is, right?
Right. If you can localize with the accuracy of the accelerator computers and all of that, the soup beams which they're using at that energy level. Yes, you can. But, you can localize. There's my soup beam here. Here's my soup beam there. It's so many angstroms in radius or whatever, and they have a certain probability to collide. and blah blah blah. I mean, all of that still applies. I'm not
No, they don't have a
negating
fair probability to collide. If it's a soup beam, there's no probability at all. If it's a soup beam, there's no probability at all.
That don't collide.
There's no chance of collision at all.
What if there was only one beam there in one direction? It's not colliding with anything. So of course there's a probability that if I have two beams, I could guide them in such a way that they never collide, or I could guide them to try to make them have a head-on collision. Again, that's all the guys at CERN. That's what they do every day, adjusting with their computers all of the magnets and everything. First to keep the beam in the ring, and then you've got two beams that are counter-rotating to guide them so that they'll collide. There's nothing particularly mysterious about that. That's just the guys fiddling with the computers and the different magnets to guide these beams. They can make them so that they don't collide. They can say, let's go out to lunch, and we don't want any collisions while we're out to lunch, or we have to shut down our computers or our sensors or whatever. And so let's keep the beams. So, but just be sure that they're in two counter-current are counter-rotating in the ring, but they're never going to collide. And then we'll just tweak the magnets a little bit to make them collide. So that, yes, these are soup beams of almost 100% concentrated quanta with no differentiation. It's just like pure energy, which I think is a wonderful idea. I don't know why they just don't embrace that right off the bat. I mean, why are they continuing to say I have protons, at 13 TeV colliding with other protons, and I get this huge spray of these jets and so forth, of zillions of other particles which continue to decay and cascade down the line. Well, I don't see why they continue to call it protons. Like, for example, if I have a picture of a face made of little black dots and then I pour black ink over the whole paper, you could say, well, there's still a face there, but, no one else is going to see the face. The face is only in your imagination.
No, I would argue at the mainstream that we continue to do that because of our intuition that we have protons and they're a fixed size, and as we accelerate them, that they don't change. That's mainstream's view. I mean, they increase in mass, but otherwise maintain their particleness. Although even from mainstream, these people can't decide whether they're particles or waves, but they are localizable in space. So why do we keep protons? Because that's definitely what our intuition says about it.
Okay, let's keep talking. This is good. I like this. You said they increase in mass.
The thing is that
what's happening when they increase in mass? We're adding quanta to the beam. We're adding quanta to the beam, and it gets to a point where all the little slots in the volume of that beam are filled, or nearly filled, and you're up to 100% possible quanta density, and there's no differentiation of electron, proton, or anything else in that. Just like you spill some black ink on the table and you can say, I see a face in that. No, you don't.
That is the very thing that we would say.
You don't see a face in
that. We don't see that non-differentiation at high speed. I mean, they accelerate other things in CERN besides protons. They can accelerate whole lead ions, for example, right? And those things maintain their differentiation at those speeds. And when they collide them, they can predict, I think, somewhat precisely.
Well, the key phrase there is at those speeds. I'm not saying that you accelerate anything at any speed, suddenly it becomes completely into an undifferentiated soup. I'm just saying that when you get up to the speed of light in your beam, you have packed that volume in the beam with so many quanta, it becomes an undifferentiated object. At lower TeV, yes, we can actually talk about, I have this gold ion or this iron ion. and I can accelerate that thing, or I can have it as a stationary target, and shoot some electrons or protons at it, and so forth. Uh, that's all fine. There's no objection to that kind of. So it's a matter of degree how much you accelerate it. When you start to get up to the speed of light, what is that mass increase? That mass increase is you're adding individual quanta per unit volume of the beam. And with full quantization, one of the very first consequences that you run into, and if you don't like this consequence, I would say you should just reject full quantization completely. But with full quantization, one of the very first things you see, well, there must be a maximum energy density, a maximum quanta density. I mean, if all the little spots where you can put a quanta are filled, that's it. So this whole idea that there's infinite density in black holes and singularity of, it's almost like a single point, or some people might even say it is a single point, but it has infinite density. These people are in la la land. They're in complete la la land. That's completely thrown out the window with full quantization. So if you want to keep the black hole has infinite density, you better reject binary mechanics full quantization like now. I mean, just forget it completely, because that can't happen.
Well, I accept quantization, but I don't accept your model that it's in this space quanta. So the way I would explain it, so I'm saying that there is no, your bit cubes are wrong. What I'm saying, so I would say as an alternative, as everyone is entitled to their own theory. So I'm saying that space is filled with these positrons, electrons. And I'm not 100% sure what a positron electron is. Eventually, it could actually become something like what you're saying are bit cubes. But given that there are positrons and electrons, any object has to push those aside. And what I'm saying is that when you push them aside, that's like stretching a spring. It stores a certain amount of energy as it goes by. So in order for the particle to go by, it has to separate these particles. It's like stretching a spring, and then when it goes past, then it returns that energy when the particles come back together, so that it preserves the amount of energy. And the amount of the amount of energy you have is dependent upon its velocity, because the faster it's doing that, the more shock you're putting into the system, the more energy it stores. So as you approach the speed of light, it becomes exponentially more difficult to do this separation. And this is actually, I think, what we genuinely consider measure of mass. The measure of mass is not a measure of matter. I think the matter within any object remains absolutely constant. But the mass, which is resistance to acceleration, increases. And the faster you are going to the speed of light, the more tension you are sticking in the ether particles as they separate and come back together. But I do believe in, say, time quantization, that these things can only happen so fast. So the fastest any particle can translate from one spot to the next must still occur in a fixed time. So the only thing that can change is the amount of tension you can put in the particles of space. So, but that preserves the proton as a proton or electron or whatever. The speed of the particle would not change its nature. I would not say that at the speed of light that my proton just becomes undifferentiated. That just wouldn't happen. It's still there, but the limit is due to how fast. This basically the quantization of time fundamentally. I think. Since time is fundamentally constrained, the length is fundamentally constrained. That gives you your top speed limit, which is the speed of light, right?
Well, it may all come down to what is quote unquote still there as you increase energy density. like in Franklin's model, where you have a cubic lattice of spatial locations that are filled with the objects that he talks about, whether they're electrons, positrons, or whatever, the Lego blocks that he uses to make atoms and atomic nuclei and so forth. By the way, I watched the video that you couldn't show some weeks ago about how you're building the nuclei, and I thought it was very, very good. I think you're on the right track there, which is similar to what I'm trying to do. At any rate, to say that it's still there is according to who? I mean, let's say every single location in your model of quantized space is filled. So what is still there? It's all filled. It's undifferentiated completely. It's just like pure energy, if you will, is the way I would call it. You might call it pure electrons.
No, that's just like a sea of sand, right? It's like it's still made out of little particles. The particles are still there. And if you stick a beach ball in the sand, then that's differentiated, right?
Well, I say exactly the same thing. Maybe it's just a vocabulary difference. In the soup beam, which is pure energy practically, nearly 100% quanta density, possible quanta density, there's still quanta there, sure, of course. That's why it's 100% quanta density, okay? So we're not saying that quanta aren't there anymore. We're just saying that patterns of quanta, which at lower energies and lower velocities can be said to be protons or neutrons or electrons, are completely indistinguishable because it's pure energy.
Well, I think that we could probably agree that weird things might happen if particles actually gained the speed of light, I suppose. I suppose in my theory that's probably okay for a particle to be moving at the speed of light. And in fact, I think that everything that does move always moves at the speed of light. It's the only reason why we don't see things moving at the speed of light is because we have these gigantic collections, and it takes time for anything to propagate across that collection. But I would say that between two electrons interacting with each other, that if they're next to each other, that interaction happens always at the speed of light. That interaction, the smallest bit, across the smallest bit of time, across the smallest bit of space, those interactions always happen at speed of light for next door neighbors, right? That's kind of how I put it.
Well, when push comes to shove, 5-10 years from now, I'll probably be dead. But at any rate, this model or that model, my model with the quanta, or other models like yours with the electron-positron pairs or whatever they are, exactly. The ones that can explain unexplained data, such as derive electric charge, derive the speed of light, derive the mass of the electron, the rest mass. These are what are the kinds of things which are going to separate the theories which are in the major leagues from theories which are in the minor leagues, and may stay in the minor leagues forever. That's why I think the CERN thing has such low scientific merit. I looked on Twitter the other day.
Mind, the major questions not resolved by mainstream are things like basic stuff, like what's gravity? Okay, that's very basic. Mainstream's got no agreement on that. Even more basic, what is charge, and how does that work? That is even a more basic force, probably the most fundamental force, really. And then,
your task is to derive the measured value of electric charge, which is has the status
not the measured value, but
unexplained data. It's an unexplained observation. So if you got a good model, you should be able to derive this unexplained, observation. which they call a fundamental physics constant, which that's their label for it in the propaganda, in the physics textbook. But I mean, what its status is in science is an unexplained observation. It's completely unexplained. Well, of course, I've derived it, and you can read the papers that do so. But
you derived it based on the. I mean, I think that's interesting. What you did there was that, you know, you start with the constants, which are the constant of length, a constant of time, and based upon that, then you can derive these other things, right? So, and I think that's true. I think that you know, regardless between your or my model, that is probably still true. That what is quantized is space and time. Now, whether you quantize it, I mean, I quantize it as just saying electrons, whatever. That's my quanta. And you can say your quanta is your spot cube, and that's also a perfectly fine quanta. They all fill space. They all, you know, in my theory, the electron, and you know, and a proton is made out of a combination of protons and positrons. In your model, the electrons it's just a different pattern in your in your spot cubes is what that is. So, but the important aspects are that it fills all of space, and things propagate from thing to thing. Right? That's in either of those models. That would still be the same case there. Let's see. We've got some other comments here before we're getting close to the end of the hour here. It says kinetic energy can probably be considered a type of potential energy, in the potential to create, measure new elementary waves, depending on the other waves in the environment. No direct energy in there. Can kinetic energy be considered a type of potential energy? Probably, I would disagree. I would say that potential energy is actually, I would almost put it in the category of fictitious kind of energy. That it's just that it's potential. If I stick an object on my hand, you know, it has, you know, does that have energy? Potential energy? You know, I would say no. It only has energy only if I take away my hand and it begins accelerating in the gravity field. That's kind of my opinion. Did anyone else have any opinion? I mean, I'm kind of saying potential energy, it's fictitious. It doesn't really exist.
Well, potential inertial mass, which is inertia being resistance to force, which you seem to agree with, inertial mass is assigning a number to the inertia. Inertial mass is inertia quantified as a number, depending on what object you're considering. Inertial mass, I've shown in my theory anyway, as being a Lenz's law force. Lenz's law says is electromagnetic law, and I believe that everything boils down to electromagnetics. Lenz's law is an electromagnetic law. It says if you move a magnet, then there's a force that counters that move. And
what does it have to do with potential energy?
Well, if you know what kinetic energy is, then you can talk about whether it equals potential energy or not. Kinetic energy is magnetic fields of the various elementary particles, protons, electrons, and neutrons, as they're in motion. And the higher the velocity, then, by Lenz's law, especially the higher the acceleration, the more resistance to force, and hence the greater inertia. So kinetic energy, being 1/2 mv squared, is in terms of the velocity of the magnet, the elementary particle magnet, and it's inertial mass, which is resistance to force quantified as a number times 1/2. Whereas gravitational mass is the electrostatic field of each little particle gives it its gravitational mass. So you see right away that inertial mass does not have to equal gravitational mass. So the equivalence principle is false. So then now you define gravitational mass and inertial mass, and hence kinetic energy. And since potential energy usually refers to the fact that you're in a gravitational field, so you've got now, you know what gravitational mass is too, you should be able to then address the topic of whether potential energy and kinetic energy are the same, because you know what each one is actually in terms of Lenz's law and Coulomb's law and Ampere's circular law and so on. So the whole point of discussing whether you've got inertial, kinetic, and potential energy in a gravitational field are the same, well, you can say no, because potential energy is with respect to the gravitational mass in a gravitational field, whereas kinetic energy is with respect to the inertial mass, which is a Lenz's law thing, where it's electrostatic mass is a Coulomb's law thing.
Okay, here, I got another interesting comment here. So this one's for James. It says, as far as I know, there's no limit observed to energy increase. That doesn't seem to fit the idea that all quantum slots can be filled. I mean, I think this is an interesting point. So what he's saying is that so far as we know, we can take a proton and shove arbitrary amounts of energy into it. And if Bill were here, he would explain that, this contradicts the idea that, you can only accelerate a particle so fast because the thing that's accelerating it only goes at the speed of light. That's not actually true. As you insert energy into the particle, any acceleration that it does get does increase the energy, and we can tell that because when it hits a target, that energy comes out, and we can see that it's a greater amount of energy. So the energy that we are putting into the particle is getting in there. It seems to rise, and there seems to be no limit to how much energy we can stuff into the particle. So that
would be a huge news. That would be huge news for CERN.
No, I think that's why they want to build bigger particles.
They've got their beams up very close to almost 100% the speed of light.
Yeah, almost, but
that's as far as they've been able to go.
That's closer. The more energy they have, the closer they can get.
So anything you read about work at CERN and other accelerators as well indicates that there is a limit to the amount of energy increase. So the idea that there's no limit, I mean, that would be huge, incredible news in physics.
Well, I think
everyone would say, my gosh, do you mean we can get our beams up to twice the speed of light? Or how about 5 times the speed of light? Let's make the ring 10 miles in diameter, and maybe we'll get twice the speed of light. Well, no one is saying that.
No, it's not that.
Everybody is sure that there's that once you get up very close to the speed of light with your beams, that's it. There's you can't put any more energy in there. So that everyone seems to agree, except the people that talk about black holes being infinite energy density. But everybody in terms of accelerator physics agrees that there is a limit to energy density.
No, I don't believe they would. I mean, we're not talking about getting faster than the speed of light. What we're talking about is the exponential increase in energy as you get close to the speed of light. And there's a big difference between 99.99% and 99.999%. That tiny bit of 0.001% increase might double the amount of energy that goes into that particle. I mean, and that's what their working assumption is, that they build the bigger accelerator means that they'll get even closer to that speed of light. They'll never exceed it, but according to the formulas of relativity, blah blah blah, there is no limit to the amount of energy that they could stuff into an individual proton, right? stick the entire energy coming out of an atomic weapon in a single proton if they got it going fast enough, right? Or at least that's what they think. Now, your theory would your theory still might be compatible with that, but we'll never reach the point where we're at the speed of light, right? See, the thing is that what you're saying about it becoming undifferentiated, that would only happen at the speed of light, really. It's anything less than that, it would still be identifiable as a point particle. So, maybe there's no
well,
real
it's more. I don't think it's an all or none thing, Franklin. In all due respect, I think it's more a matter of degree. Like, for example, if I have your newspaper print picture of a face that is easily recognizable, but if we look close under a magnifying glass, we see, gee whiz, it's just some black dots here and there. But if we step back, I can see that it's a face. It's depicting a face. But so it's a matter of degree as you start to randomly fill in the white spaces with additional black dots where, let's say, a sample of college students that they are guinea pigs will actually see the face. How far can you obscure the face in a whole lot of additional black dots before none of the college students see a face in there? They just see like a fog or whatever.
Well, I don't think it has anything to do with addiction at all. I mean, I guess that would be kind of the advantage with my mechanical model, in that I don't have that kind of density thing to worry about. I just have positrons, electrons, and they have to get out of the way. So that's. But that's how we compare and contrast, right? I mean, you're
well, think about it. Every slot that could hold a positron or electron was filled, and then you're getting up to the idea of maximum energy density or maximum electron.
Well, I generally feel that is the normal case. That's the normal state of affairs. That all of empty space is filled with basically. The maximum number of
okay, all right. According
to equilibrium conditions, is what it is. I mean, that's how my theory works. That all of space, is
so there are no empty spaces. Okay, there are no empty spaces.
There's no empty spaces. I mean, there's.
Well, then how do you differentiate anything?
Well, you differentiate a thing by groupings. So you have. Because you're
so there are some empty spaces.
Well, there's
the only way you can have groupings is that some of the spaces are empty.
Because we've had this big discussion in the email about what I mean by the void, right? Okay, I'm saying that the void does exist. I mean, you have your positron, your electron. It's a little ball. There is some void space between them, and these things are constantly moving, just like they are in the atmosphere. So my analogy to vacuum space is just like the atmosphere. You've got these particles, they're moving around and they're just bumping into each other. So there's space between them. That's how we can move through the atmosphere, because they get out of the way. They're not so packed together so tightly, like, if they were like solid cubes and there was no space between them, then that would be a solid. And that's definitely not what we have. I think what we have is more like a gas. So the gas gets out of our way. They're not glued to each other. So, and we differentiate the presence of a electron because it's an independent particle. Therefore, it has a charge compared to the atmospheric ether, which is neutrally charged because it's made of positrons and electrons. That has no charge. Or we can recognize the proton as being a combination of two positrons and electron, which I kind of think is probably in a dumbbell formation. Probably have a central electron, two protons attached to the side somehow. And that's how we differentiate when there's a proton present. And then you can build all the atoms out of protons and electrons. And in my world, the neutron is actually the same thing as the ether particle. There's actually no difference between those two. So effectively, you could say that space is a sea of neutrons, is another way of putting it in my parlance. you can just think of a neutron gas. So that's how I kind of think of it.
Well, we're getting toward the end. So one summary of the big picture is to say, meanwhile, in the mainstream physics media, the standard model is the going model, and they're very happy to so-called complete it with the Higgs boson. Now, they admit that there's some 19 or more constants, which are basically, I'm calling them unexplained observations, like the speed of light, alpha, electron rest mass, etc. There's about 19 of those which are required to make this standard model work. All my message is, I think it should, well, in other words, the standard model people agree with my point of view that it is very worrisome that you've got 19 so-called fundamental constants, which are actually unexplained observations in my book, and they are totally unexplained observations. So I think the breakthrough is going to come when somebody, such as some of my work in the binary mechanics, or perhaps some of you all, actually explain some of these unexplained constants. In other words, derive them from the first principles of your model. And that's where the fruits of the tree come in terms of determining which model is the one that is ultimately going to win the World Series of physics, as it were.
Okay, well, it looks like we are at the end of our time here. So just to summarize a little bit, I think we started off the discussion about gyros and how those things can possibly work. And so I don't think very, very mysterious thing here. And I tried to come up with like some analogies as to why the gyro does what it does. But even to me, it's still, quite a mystery as to how the gyroscope can maintain its position. And then we started to discuss, what is a laser ring gyroscope, which doesn't have any spinning things, but yet can still detect its orientation in space, and that there must be something in space that it's doing its work relative to. And then we started talking about relativity, and does the speed of light get added to the thing that is doing the transmission or the receiving, which would seem to be the case in a ring gyroscope, because that's what the entire thing is based upon. But then we argued that speed of light is more like speed of sound in air. It's relative to the medium that you're sitting in, and then got into a little bit about how the GPS sees the world. What the GPS sees the world as stationary but rotating 24 hours, and that's probably. That makes the geocentrists really happy, but the rest of us probably don't think that's true. And that you'd have to do things like the Earth is like in its own little bubble of ether to explain, what's going on with the GPS. And then we got a little bit into what's going on with like relativistic mass increase, so that the Newtonian mechanics, 1/2 mv squared, seems to work fine, except when you get into really high velocities, in which case the m seems to increase. And why is that? And James pointed out that in his model, that he thinks that all of the bit spots at that accelerator, because apparently the velocity corresponds to the bit density. And as you approach the speed of light, that bit velocity approaches 100%. So he thinks that the protons aren't really there. That is ridiculous for people. It's starting to say that they're colliding protons at that point. So, as I understand it, but I argued that no, I kind of agree with the mainstream there. I think that there's still protons there, but it may be, as I said, an amount of degrees, and probably we're still not nearly close enough to the speed of light where maybe these things make a difference. I don't know. So I think that's where we went for this week's 2 hours of discussion. And thanks for everyone participating, and hope to see you here next week then. Okay, so bye-bye.